Hello everyone, I'm Riwa Younes from Group W. My matric number is B0323202127. So today I will provide an overview of MIPS assembly language and its relevance in programming and computer architecture. MIPS assembly language is low-level programming language designed to communicate directly with hardware. Its key feature, it is minimal abstraction enabling efficient and precise control over system operation. So some of its key characters include direct execution on microprocess and an extensive register set that allow multiple concurrent process, thereby enhancing system performance. So why does it matter? Maps provide invaluable hand-on experience with low-level programming, offering insight into the crucial interaction between software and hardware. So the knowledge from the foundation of understanding how systems truly work. To move from program workflow, so we have input phase. The input phase, the program begins by promoting the user to input 10 numbers. These inputs are validated to ensure they fall within the range of 0 to 255. Valid input are then stored in array from further processing. Processing phase, the stored number are iterated through one by one. Each number is then converted into its binary, octal, and hexadecimal representation. So output phase, finally, the program display each number in four formats: decimal, binary, octal, and hexadecimal. These steps ensure clarity and allow user to validate the conversation. This workflow illustrates the seamless integration of input validation, data processing, and output generation in structured and efficient manner.
My name is Liqa Muhammad. Here is a snippet of the code we used. It include message for user prompts and error handling, arrays to store the numbers, loops to process and convert the numbers, system calls to display the results. The program validates user inputs to ensure they are within the range of 0 to 255. If the input is invalid, it displays an error message and asks the user to try again. Our program has three key functionalities. The first one is binary conversion, converts numbers into 8-bit binary format, which is useful for hardware. The second one is octal conversion, breaks numbers into base 8 components using modular arithmetics. The third one is a hexadecimal conversion, generates 2 digits hexadecimal values, mapping digits 0 to 9 and letters A to F. For each build input, the program displays the binary representation 8 bits, the octal representation base 8, the hexadecimal representation 2 digits. For example, if the input is 8, this is the binary convert and octal convert and hexadecimal convert.
Today I'll be presenting summary and conclusion. This project focused on implementing number conversion into binary, octal and hexadecimal format using MIPS assembly language. This project aimed to showcase our understanding numerical system and the practical application of assembly language in computer architecture. Let's go through the key feature and result of our work. This project is designed to convert number into three formats: binary, octal, and hexadecimal. Each conversion was structured in the program to ensure clarity, functionality. The core feature of the program include binary representation in an 8-bit format, octal conversion hexadecimal conversion in a 2-digit format. We made sure to standardize the code and explain each section consciously for clarity. Let's start with the program header. It serves as the introduction of the project, providing a brief description of what it does and listing the team member involved. The header is essential for identifying the program scope and providing context for the code that follows. Moving to the binary conversion. The binary conversion processes each bit of numbers sequentially, converting it into an 8-bit binary equation. We ensure that each step of the conversion is handled carefully, ensure that numbers are correctly represented in the binary format. This is particularly important when working with low-level programming, as each bit is significant. Next, we have the octal conversion. The program breaks the number down into base 8 components and calculates the result. This process involves dividing the number by 8 and collecting the remainder. It's an essential skill in assembly language programming because the way numbers are represented at the low level of memory. For the hexadecimal conversion, the program converts the number into 2-digit hexadecimal format using positional division. Each remainder is mapped to its corresponding digit, including value for A through F. This step demonstrates how we can map number to a higher base system, and it's crucial in understanding how computer systems handle large data. We also took great care to verify the output, ensuring that the result matched the expected output for binary, octal, and hexadecimal format. This step is key to ensuring that the program is working correctly and providing the intended functionality. The correct numerical representation for user input were constantly produced. Conclusion. In conclusion, this project not only demonstrates our understanding of MIPS assembly language but also highlights the practical application of converting number into binary, octal, and hexadecimal format. This fundamental concept of numerical system and their role in computer architecture. The project reflects our attention to detail, programming skill, and the importance of clear documentation and structured code.